Welcome to The Explainer. Today, we are diving into a really strange and powerful world. A world where electricity can flow forever, where magnets literally float in midair, and where the normal rules of physics, well, they just seem to break down. This is the incredible world of superconductivity, a state of matter that lets energy move with perfect, almost impossible efficiency.
So, what's on the docket? First, we're going to get our heads around what perfect conduction actually means. Then, we'll get to the fun part, the magic of levitation it creates. After that, we'll look at the very strict rules that govern this power, and we'll peek into the quantum secret that makes it all possible. And finally, we'll see how this totally bizarre science is already shaping our future.
All right, let's start with the big idea. What does it really mean for a conductor to be super? You have to imagine a perfect, totally frictionless highway for electricity. No traffic, no bumps, no energy loss.
Think about this for a second. If you start an electrical current in just a normal loop of wire, that current dies out in, a fraction of a second because of resistance. But in a superconductor, that exact same current, once you get it going, could circle that wire for, and this is not an exaggeration, thousands of years, without stopping, without losing a single drop of energy.
This isn't some sci-fi concept. It's the reality of superconductivity. Now, we're not talking about low resistance. We're talking about a complete and total vanishing act. You take a material, you cool it down below a very specific, very cold point, its critical temperature, and poof, all electrical resistance just ceases to exist. This number says it all. When scientists first tried to measure this, their instruments just kept reading 0. They honestly thought their equipment was broken. But it wasn't. The resistance drops so close to 0 that for all practical purposes, it's just gone. And you might be surprised to hear this isn't some brand new discovery. This effect was first spotted way back in 1911, but understanding it, that took decades. It led to a Nobel Prize-winning theory and kicked off a relentless, ongoing search for materials that can do this at more practical, everyday temperatures. And here is where things get really weird and counterintuitive. The materials we think of as the absolute champions of conductivity, copper, silver, gold, they don't superconduct at all. In a strange twist of physics, many of the best superconductors, like lead or niobium, are actually pretty crummy conductors at room temperature. But here's the thing. Zero resistance is only half the story. The property that truly sets a superconductor apart, and the thing that makes it look like straight-up magic, is its bizarre relationship with magnetism. It's called the Meissner effect. And here's what happens. As a material cools down and becomes superconducting, it doesn't just block magnetic fields from getting in, it actively kicks out any magnetic field that was already inside it. It just purges it completely, creating a perfect magnetic void inside. And this is the crucial point. This is what makes a superconductor truly unique. See, a hypothetical perfect conductor would just trap any magnetic field inside it forever. But a superconductor, it basically acts like a bouncer. It tells the magnetic field, get out and stay out. And this powerful expulsion of magnetic fields leads to probably the most stunning thing you can see in a lab, the ability to make a magnet levitate. The superconductor repels the magnet's field so forcefully that the magnet just floats. It hangs there in midair. It's a direct, visible consequence of this incredibly deep quantum effect. So, if this stuff is so amazing, why isn't everything we built made out of it? Well, that's because this special state is incredibly fragile. It's a real diva. It can only exist under very specific and very demanding conditions. First, and this is the big one, it has to be incredibly cold. Every single superconductor has a critical temperature that it must be cooled below. For the first materials they found, this was just a few degrees above absolute 0. I mean, unimaginably cold. Even the so-called high-temperature ones still need to be dunked in liquid nitrogen to work. Second, it's really sensitive to magnetism. So despite its amazing ability to kick out magnetic fields, if you put it in an external field that's just too strong, what we call the critical magnetic field, the superconductivity is instantly destroyed. The whole effect just collapses, and the material goes right back to being a normal, boring, resistive conductor. And finally, even with 0 resistance, you can't push an infinite amount of current through it. And why is that? Well, because a moving current creates its very own magnetic field. And if that current gets too high, the critical current, its own self-generated magnetic field will become strong enough to kill the superconducting state. It basically becomes its own worst enemy. So you should think of these three things, temperature, magnetic field, and current, as a boundary.
a sort of three-dimensional box. As long as you operate inside that box, you have this incredible phenomenon. But the second you step outside any one of those boundaries, boom, it's gone, instantly.
Now, based on how they react to magnetic fields, we sort them into two types. You've got type 1, the purest. They're all or nothing. They expel the magnetic field completely until they suddenly just break. But then you have type 2. These guys are more pragmatic. They enter a mixed state, and they allow the magnetic field to thread through them in these tiny, controlled little tunnels. And this clever trick lets them withstand far stronger magnetic fields, which makes them the absolute workhorses for powerful stuff like MRI magnets.
Okay, so how? How does any of this work? How can a bunch of electrons just suddenly decide to stop resisting and flow perfectly? The answer is a really remarkable bit of quantum teamwork.
The heroes of our quantum story are called Cooper pairs. See, normally electrons are these grumpy loners. They fly around, they bump into the atoms in the material, and that's what creates resistance. But in a superconductor, they team up. They form a pair, bound together by interacting with the vibrations of the material's own atomic structure, vibrations we call phonons.
And the Nobel Prize-winning BCS theory explains how this happens. It's brilliant. First, the electrons pair up. Second, these pairs drop into a special, protected, low-energy state. It actually takes energy to break a pair apart, which creates what's called an energy gap. And finally, all of these pairs move together. Not as individual particles, but as one single, coherent quantum wave that just flows effortlessly through the material, not hitting anything.
And the real smoking gun for this theory was something called the isotope effect. Scientists figured out that if you take a superconductor and you replace its atoms with heavier versions, heavier isotopes, the critical temperature goes down. And since heavier atoms vibrate more slowly, this was the proof. It was the evidence that those atomic lattice vibrations were the glue holding the Cooper pairs together.
Okay, so this is not just some bizarre theory for physicists to argue about in the lab. This quantum weirdness has actually enabled some of our most advanced and most powerful technologies.
So where do we actually see this stuff in action? Well, think about medical MRI machines. Those incredibly strong and stable magnetic fields are only possible because of superconducting wires. Or what about the giant electromagnets that steer particles at nearly the speed of light at the Large Hadron Collider? Yep, superconducting. And looking to the future, they are absolutely essential for the next wave of tech. Everything from frictionless maglev trains to the fundamental building blocks, the qubits, that will power quantum computers.
So, what's the big takeaway here? Superconductivity is not just a lab curiosity. It's a real glimpse of quantum mechanics working on a scale we can see and use, and it has world-changing potential. Just imagine a power grid that loses zero energy between the power plant and your home, or computers that operate on a totally new level. That is the promise, and that is why the search for a room-temperature superconductor isn't just some academic hobby. It's one of the greatest technological treasure hunts in modern science. What will our world even look like when we finally find it?